So we're talking about quantum mechanics. And is it true, Monica Soto Ruiz, that we know everything, that you can pull one book off the shelf and it's going to have all the answers to, my goodness, light, gravity, this stuff? No, right? In fact, if you're going to talk about what's going on at the molecular level, what's going on with matter, you got to pull the book off the shelf, quantum mechanics. But has yet to be proven wrong, though. So, but it's everything. I mean, it's everything that regarding why things happen in nature. It's matter itself, and why it behaves the way it does. Okay. So what they did in quantum mechanics, if you remember, Paul, the technical jargon is the Schrödinger equation was solved for wave mechanics for what atom? The only part I'm interested in you knowing is the atom. What atom could they actually figure out in quantum mechanics and get actual numerical solutions for? Which one was it? It was hydrogen. Why? It only has one electron. So in order to understand why this is so bloody complicated, you pretty much have to take the course. But that's not really what I'm driving at. What I'm driving at is we can only solve it for one atom, one element. So we're going to use it to describe every other element known to man. Iron, copper, cobalt. We're going to use hydrogen solutions. And we're going to write things called electron configuration. Well, Jasmine, what's the big deal about electrons? Why not worry about the protons and that sort of thing? Why all this talk is about electrons? Electron configuration here, orbitals, it's all electrons. Does anybody, if we want to talk about protons interacting and things, we need to be talking about the end of the world, nuclear war. That's the only time you're going to be talking about neutrons and protons doing stuff. Otherwise, it's chemical reactions. It's matter interacting with matter. It's all electrons. Electrons are doing everything. Okay, it's all about electrons. And that's why we're talking about, an electron configuration. How are these electrons, what are their energies? This element, what electrons does he have and what energies are they? How are they behaving? So we can use it to predict what's going on in nature. Okay? So this diagram, this is the solution for the hydrogen atom. Okay? And it says, Kelly, an electron configuration consists of placing all the electrons an atom has. So, Kelly, I don't know, look at phosphorus. How many electrons does phosphorus have? 15. Good, she's looking at the number right up there, 15. So phosphorus, it has 15 electrons. We're going to put it in the orbitals, right? And the result is the electron configuration. And we're going to start from the lowest to the highest energy. So if you see like there's 1s, then there's 2s, then you'd fill probably what, Alyssa, after the 2s? Probably fill the 2p, because he's next in energy. So you're just going up in energy as things go, and then you'd fill the 3s. Okay, but each little line, you have to look really hard at this, Caroline. Each little line is an orbital. So it looks like the 2p has how many orbitals? 3 of them, right? Now, how many electrons, Eric, can I fit in any single orbital?
Is it the number?
Yeah, how many?
Does it go with the ends?
No. That'd be a good one. I should have put those in the options. They're not possible answers.
Oh.
I just added this morning. What would you guess?
2.
Yeah, good. Go buy a lottery ticket today. 2, right? That's it. 2 electrons in every single orbital. Okay, so we're going to be filling them up. And so you're going to start with the lowest energy one. But how do you know the order in which to fill them up? We have two options, right? Because I'm saying you start with the 1s and the 2s and the 2p. I see two options here, Priscilla. You see these two options, just looking at the little diagrams here, which one looks the best, option 1 or option 2? Option 2, because she sees the little smiley face thing, right? So definitely we're going to be doing option 2, unless you have a photographic memory. Just take a picture of this. That's it. Those are your answers. Like we said, you do the 1s first, and the 2s, and the 2p. And the 2p has 3 orbitals in it. How many electrons are going to go in here before it's full? If there's 2. If there's 2 in each orbital. But there's 3 orbitals, 6. So they're going to be done when you fill in with 6, right? So that's one way to answer it, but got a photographic memory, great. Otherwise, we're going to do it this way. Know how to use a periodic table to write an atom's electron configuration. So we're going to do the exact same thing that chart did, except use a periodic table, because that's given to you in all the quizzes and exams. What's first? What's first? According to this chart, you're supposed to fill what first? What orbital? 1s. So you fill 1s first. We're going to start at the top. That's where the 1 is, right? But there's how many electrons in every orbital? 2. So that means you keep... Helium is still 1s then, because here's 2 is way over there, right? And then Monica Soto Ruiz, what do we fill after the 1s? 2s. Okay. There it is. 2s. And then after the 2s, Paul, is what? 2p. Keep going. All right, now we're at 2p. So I'm following the numbers here, right, on the periodic table. 1, 2, 3, 4, 5, 6. Right? Jasmine, what goes down here? 3s. So do you see kind of what's going on? Over on the far left, 1s, 2s, 3s, probably 4s, 5s, 6s. Just fill them in. So probably 2p, 3p. Oh, and those are supposed to be tiny p's, aren't they? 4p, 5p, 6p. Now, Kelly, what is filled after the 4s? According to that big chart, 3d. This is supposed to be 3d. Okay. Well, if that's 3d, what's probably below it? 4d, good, and then 5d. Okay. So know this. And you're going to see how to use it pretty soon. But know that this is the backbone of everything we're doing here. Okay? The periodic table is already organized this way, because the electrons are where it's at. Electrons are why everything behaves the way they do. So that's why the periodic table is organized the way it is. So rules in writing electron configurations of atoms. Now first, just what the heck is an electron configuration? Well, we've seen that either from the periodic table, you're supposed to fill 1s first. And then you're supposed to do 2s. And then you're supposed to do, what's after the 2s? 2p. And there's supposed to be 3 boxes. And you keep going on and on and on, right? 3s and stuff. So you're filling this stuff up. If we wanted to fill it up with, I don't know, nitrogen has, Alyssa, nitrogen has how many electrons? It's 7. Yeah, you're supposed to look at the little guy up here, right? 7. Okay. So, and how many go in each orbital? 2. So, they like to do these little arrows. I don't know if you've seen this before. So you can do double-headed arrows, but I think they like single-headed arrows. Fine, right? And they can never be pointing the same direction in the same orbital. So, boom, boom, and keep filling this stuff up. And we want to do 7 of these arrows. That's 4, 5, 2, 4, 6, 7, something like that, right? Now, I'm obeying rules filling this up. This Pauli rule, it's easier, I think, to break a rule to see what to do rather than following a rule. If I want to break that Pauli rule, this would be breaking the rule. 2 electrons in the same orbital have exactly the same quantum number. That's the technical jargon. The easy way is just looking at it saying they're both pointing in the same direction. They're exactly the same. Now you can't have it. Okay?
So 2 electrons in the same orbital.
2 electrons in the same orbital cannot be pointing in the same direction. That's a Pauli exclusion principle. Was there any magic way of filling these things up? Right? 'Cause nitrogen had 7. Now let's talk. So that's this guy's rule, Pauli's rule. Does that make sense? There's another rule, Hund's rule. Okay. Now, Alyssa said nitrogen had 7 electrons. I put in, let's fix this guy. Let's go back to the way it's supposed to be. Okay. I've used up how many so far? 4, right? And then you pretty much follow that Pauli's rule to put these guys in. But then when you hit a subshell that has more than 1 orbital, you got to follow Hund's rule. And because if you look at it, I mean, I could do whatever I want here. I need to put in 4 of them. I need to put in 3, right? 1, 2, 3. I can put it that way. I can put them in this way, right? There's a whole bunch of different ways, right? So what you're supposed to do is know some of those were more higher energy than others. There's only one that's a low energy. For example, this one, 1, 2, that's a higher energy than the other, than another configuration. And Hund's rule is all about telling you the lowest energy. The reason why I'm bringing all this up is because if we would have had that, remember that tube? We had a gas in there, high voltage across it. It's showing out all this light. You looked through a spectroscope and you saw all those lines. You didn't see every color known to man. You just saw certain colors in there. Well, maybe for nitrogen, this is a higher energy. That orientation, that configuration jumps to the lowest energy. All in the same direction, either all up or all down. So it reconfigures to this. And then it lets off a little green light. Whatever, right? But, so what I'm driving at is there's a whole bunch of possibilities. What's after 2p? 3s. Heck, erase one of these dudes, put them in there. There's nothing wrong with doing that. It's just that it's not the lowest energy. After 3s is, what's 3p? 1, 2, 3. Let's erase one of these dudes and put them way up here. Nothing wrong with doing that, right? Except this is how we generate those lines. Now, all these possible exchanges aren't possible. It gets complicated, but the point is let's write ground state, the lowest energy. That's what this is all about. So the lowest energy, I need 7 electrons. So I erase all this high energy stuff. It's not even, right? And I want them all pointing in the same direction. That's the lowest energy. That's Hund's rule. So breaking Hund's rule would be something like this. That's breaking Hund's rule. Make sense? So when you write these electron configurations, we need to follow the Pauli rule and the Hund's rule. Okay. So they call this, with the arrows, when you do the homework, with the arrows, they're going to call that a diagram. Write the electron diagram or the orbital diagram. That means draw the lines and the arrows. But if they say electron configuration, no arrows. Right? Instead, you just list them all out. 1s, 2s, 2p. After that was 3s and 3p. Right? You list them all out. And nitrogen has how many again? How many electrons? 7. So you just fill them up this way and make them superscripts. So there's 2 in the 1s, there's 2 in the 2s, and in the 2p there's how many? 3. There's 3 more to go to get to 7. So you put a 3 there, and there's none here. So the guys with zeros, they never write them. They just leave them out. So when they say electron configuration, this is what they're talking about. Okay? So let's write the... Now again, when they say ground, it's important really that they say ground state, because you could write pretty much anything you wanted if they don't say ground state. And I can't mark it wrong. So as long as you obey the Pauli rule. Okay, right, the ground state electron configuration of arsenic. Okay, so find arsenic. How I like to do this, Caroline, is find arsenic on the periodic table. What number is arsenic? 33, and it's right here. Okay, so we're going to write arsenic equals, and we're going to keep filling up these orbitals until we stop when we hit arsenic. So what are we, Eric, what are we supposed to be filling first according to the periodic table? The 1s. And we keep going, it's full. And then after the 1s, Priscilla, now we're filling 2s. And then up here, everybody, this is going to be 2p. And how many am I filling in? 2p. I got to keep going until I stop at arsenic. And if you're not sure if it's what the number is, you can just count it. 2p1, 2p2, 3, 4, 5, 6. All right, so I got them still going. Now I'm filling 3s and 3s1, 3s2, 3s2. Still not at arsenic. Everybody, this is going to be 3p6. Monica, did you see how, Lopez, see how I got that? No? We just filled up right here. This guy. Right? We just filled him up. So you have to know that this is 2p, this is 3p, that's 4p. If you don't know it, you're screwed. Right? Is the number of electrons. Right? So we still can't quit yet because we're at 3p6. If we quit right now, we just wrote whose electron configuration? Argon, right? You see that? We got to keep going. So this, everybody, is 4s2. Don't stop there, otherwise you're at calcium. Now we're in the D's. 3d10. If you don't even remember the number, just count them. 1, 2, 3, 4, right? 10. 3d10. Still got to keep going. 4p, sorry, 2p, 3p, 4p, how many? 1, 2, 3. 4p3, right. It's a lot, right? Okay. But there's an easier way. Because this gets, I mean, just imagine writing radon or something, right? I mean, this is going to get long. It's going to take forever. So there's a quicker way. Noble gas core notation. What's so special? Do you remember, Summer, about the nobles? What's so special about noble gases? They don't what? Or supposedly, they don't react with anything. Because their electron configuration is extremely stable. It's packed in tight. You can't, their electrons won't do anything because electrons don't do all the reacting. So here they are. They don't do anything. So what you do is, for arsenic, if you want to do the noble gas core notation, you write its nearest noble gas in brackets. And then you write the remaining, what's left over, orbitals that are left over. So if you find arsenic, Monica Soto Ruiz, 33, what would be its noble gas core? Its nearest noble gas is what? It's either got to be this one or it's got to be that one. There's only one right answer. Which one would it be? got to be the one before it, because it doesn't have enough electrons to be this dude. So it's got to be the one before. So you have to go backwards. Argon. So you put argon in brackets. And then you do everything you just did. Then you start, exactly, then you just start over here. But at least you get to skip a lot, right? Okay, so now we got to start over here. Now this was, yeah, because the number's right there. That's a 4s2. And then everybody, 3d10. We're almost there. 4p3.
So then we don't have to put groups above?
No. In fact, all of this stuff right here, that was all my argon. We got to skip all of it. Okay. So that's writing ground state electron configurations, both with and without noble gas core notation. Okay. One more concept, valence electron configurations. We have this whole big electron configuration, Paul. I said electrons are supposed to be doing everything, all the reacting, why there's colors, they give all the properties of these substances, everything. What? Which electrons? All of them? Or is it only going to be which electrons are the most energetic? The highest ones, the ones way out here, right? They are going to do everything. These other electrons, you can call them the inner electrons, and physically they are, man. They're even closer to the bloody nucleus, and who knows where they are? They're in there 99.9% of the time. But the point is they're in there. The ones that are farther out, higher energy, moving around so much faster, those are the reactive ones. But they don't call them the reactive ones. They call them the valence electrons. Okay. Now there's a trick to figuring out what these valence electrons are. Okay? I don't think this is the trick. This is the terminology. It's the valence electron configuration are the ones, all the electrons that are outside of the noble gas core or the pseudo-noble gas core. So that would mean that if you want to write the if you want to write the valence electron configuration of arsenic, it should be all this stuff, right? Doesn't it look like that would be your answer? Because that's everything outside, but it's not your answer. So I think the trick to doing this is using the periodic table. The periodic table knows that, man, it's the valence electrons are everything, because that's the only thing that does the reacting. So do you remember these groups? Oh, all these alkali metals reacted with water. That means they have the exact same number of what electrons? Valence electrons. They also call them outer, but valence electrons. All these guys have one valence electron. All these guys have 2. All these have 3. That's the game that they're playing. Boron, all of them are, no, not, you have to use the Roman numerals. To read the valence electrons, you got to look at the Roman numeral, not the, what's the word for a regular number? If there is one. Right? You look at the Roman numerals. So for carbon, its group, they all have how many valence? 4. Right? Okay. So let's find arsenic. Arsenic has how many valence electrons? 5. That's how I figured this out. Okay, so I know this is arsenic, but it only has 5. So looking at this, how can I get 5 electrons? Combine which 2 probably? The 4s2 and the 4p3, because it's those superscripts that are the number of electrons. So my answer is 4s2, 4p3. Okay, that's how I do it. But you could also do it the definition way. The definition way is everything outside of noble gas core, so that means don't look at argon, and pseudo noble gas core. That means don't look at D10. D10 is very full, very stable. So it's everything outside of noble gas core and pseudo-noble gas core. Same, you get the same answer. But I think it's safer over here because the periodic table tells you, oh, I have to have 5. But whichever you prefer. All right, if you want to do the deal, if you want your exam, you got to go to the boards. You go to the boards, you get your exam back. All right, wait till Monday. Alyssa, you can do it. Don't be so lazy. Well, you don't have to get it, but you can still participate. Okay, on his very first one, write down the letter A, B, C, or D, which is not allowed. Let's do not allowed. So write down A, B, C, or D for each configuration that is not allowed. Now, if you didn't bring your little outline, I can shut off the lights here, make it easier. Right? Okay. According to Pauli's rule, Pauli exclusion principle. Oh, you remember which one that was? Hund is the one with, you got to spread them out to get the lowest energy. Pauli was the one where no two quantum numbers could have the exact same, could be exactly the same. Two arrows couldn't be pointing in the same direction in the same orbital. That's the trick, though. They got to be in the same orbital. So is there anything wrong with A? Yes. Most definitely, right? So you should have wrote down A. Is there anything wrong with B? No, there's not, right? Because these guys are in different orbitals. So they're fine. Is there anything wrong with C? Yeah, look at that. They're those two. Okay. Is there anything wrong with D? No. Oh, hey. But D would not be obeying whose rule? Hund, right? But it's possible. It's just not the ground state. But we're not talking about Hund's rule, we're talking about Pauli's rule. Okay. Right, let's try this next one. Write down A, B, or C. Which of the following electron configurations are possible? Are possible. Which of the following electron configurations are possible? A, B, or C, or all three? Write down the ones that are possible. If you don't know, just ask Kelly. She already has her answers down. All right. You got to write down what you think. Got to make some statement here. I think everyone's got something written down. Okay. Is B possible? Why not? Why or why not? Yeah, you can't have 7 in a P. Good. So B is not possible. A is not possible. Is B possible?
Yes.
B is possible, right? It's just not the what state? Ground state. Now you can stick these dudes wherever you want. You can pull one out of the 1s and throw them way up into the 5D. I don't care. It's possible, but it's not ground state. Is C possible? Yeah, C's possible. Okay, good. So keep going. Let's try EX3. All right, this is going to be a long one, so someone write high, someone write low if you're right next to somebody. Write the electron configuration of the ground state of iodine, right? Both with and without noble gas core. So write it without noble gas core first, and then write it with noble gas core. Well, I'm only going to ask you to do this once. But if you do it once, it's a lot of work, and you're going to remember it. Because look where iodine is. Right? both with and without noble gas core. So I want do the long way first. You'll appreciate it. Do the long way first. All right? It's good practice. And then you'll never have to do something this long again, I don't think. Right? So you're starting out with 1s2, and then, yeah, good. You got it. And then 2s2, and keep going. And what's helpful, 1, 2, 3, 4, 5, 6. There's 6. Now, what will be really helpful when you're doing this, I think, is don't be looking at your notes. Instead, be looking up here and be able to picture 2p, 3p, 4p, right? Because that's what you want to be able to do. Use the periodic table. Try not to use that little cheat sheet in your notes, right? Because these are all 1s, 2s, 3s. These are 3ds, 4ds, 2p, 3p, 4p, right? And just keep filling up until you hit iodine. Okay. So they want the electron configuration. So you have to do 1s, no diagram, 1s2, 2s2, 2p6, and keep going. Yeah, P's have 6. Good. Keep going. And then if there's 3, because where you're at is you're right here, right? Yeah. 3D. Yeah. And now you're filling up this guy. Yeah. He's 2p, 3p. He's 4p6. Okay. So then it would be 4p6, and then it would be, what is that, 5s2, and then you keep going. So get used to using the periodic table. Get used to using the periodic table for this. And Jared, no commas. They don't like commas. 5p5, is that right? 2p, 3p, 4p. Yeah, looks good. I don't know. Let's see what Monica 2 gets. Yeah, you should have 4D too. 3D, 4D, 3D, 4D. Oh, no. 3D, 4D.
Because it moves down.
Yeah, it's 3D and then 4D. Looks good. I think so. Okay, did you get them all? Oh, you went too far. 1, 2, 3, 4, 5. 2p, 3p, 5p5. All right, so hopefully you stopped at 5p5, right? D's go 3D and then 4D. Yep. Then do the noble gas core notation 1, 2. Okay, now you have 4p6, 5s, and then it's 4d, right? Because it goes 3d, 4d. So after the 5s, it's easier over here maybe because they're kind of numbered, but 5s, 3d, this is 4d. Or you could number them on here, right? Number 1, 2, 3, 4, 5. All right, did everybody get it? Got the both with and without noble gas core notation? Good, she got it. Okay. So if you got it, I think everybody did. Try EX4. Try EX4. Period 5. It's right there. It's at number 40. Period 5, 4B. What would you expect for the valence shell configuration of zirconium? So they want the valence electron configuration of zirconium. What would it be? Yep. I changed it. So I wanted to make sure we did. Yeah, I wanted to make sure we did this one. I changed the numbering a little bit if you're following the outline. So we're doing, this is the zirconium question.
The valence-shell configuration.
Good. Now Eric caught something right off the bat. Whatever you write, your answer had better have 4 valence electrons in it. Whatever you write, your answer had better have 4 valence electrons in it. So they're not asking for the whole electron configuration. They're just asking for the top 4, right? Because it's the outer, it's the valence electron configurations. So take a look at zirconium. If you have to write out the whole thing to figure it out, fine, do that. Or if you have to write out the noble gas core notation to figure it out, fine, do that. Or
So we can only have 4 arrows?
you can only have 4 electrons in your answer. Now they don't want the, they said configuration summer, so they don't want the arrow diagram one. They want the one where you write, 2s2 and that kind of stuff. So I think for me, I think a starting point would be to write the noble gas core notation of it. I think it would really be helpful to write the noble gas core notation of it, because I think that, because then you know what not to include and that sort of thing. And you've got something written down too. So you're starting with krypton, right?
Yeah.
Okay, so what do you fill first? These 2 and then those 2. So what is this?
That's
5s
5s2.
So don't forget to write that down.
Oh.
Yeah.
And it would just be
Oh, not a 2, Priscilla. You have a 2. That's going to be the 5. Yeah.
Like, if you saw the noble gas, like this one.
That's for like D10.
Oh, okay.
We don't have a D10 to worry about.
So if it's less, so if the D is less than 10, we can use.
Oh yeah.
Okay.
Actually 5 too. They also count 5 as a pseudo sometimes.
Oh.
But you're fine. All you try to do is match this number up here. Match those Roman numerals. That's really all you do. Then you don't need to worry about it. Okay, so now if it wants the valence shell configuration. In your answer, you can't have krypton in it. You have to make sure you erase that, because you just wrote the full noble gas core electron configuration of it. So you got to make sure you erase krypton. And then you have 5s2, what is it? 4d2. So you got to make sure he's not there. Okay. All right. Let's try this one. They're playing with terminology a little bit. What would you expect for the configuration of outer electrons of manganese? They want what electron configuration? Yeah, what is it called though? It starts with a V. Valence. They want valence for manganese. Now where the heck is manganese? Oh, it's number 25, right? It's number 25.
Okay, so 7.
So we couldn't do the short
Well, what you could always do is write that shorthand noble gas core notation, then just erase the noble gas. Oh, it's manganese. It's manganese, though. It's Mn. So that might be a different spot. It should be with a 4s2. Yeah. So everybody got it? And then good. Then you erase the noble gas core. Right? 4s2, 3d. 5. Good deal. All right. Last one. Let's just do it with the noble gas core. You got the idea, right? Let's just do it with the noble gas core. Then we'll call it a day. Cobalt, noble gas core notation. Yeah, cobalt is CO. CO, and that's number 27. All right, 4s2 3d7, is that right? I can't count. 1, 2, 3, 4, 5, 6. Whoop, 1, 2, 3, 4, 5, 6, 7. 4s2 3d7. Yeah, 4s2 3d7, right? I don't know, my brain couldn't see it. Okay, so that's it. They're not asking for valence.
That rule doesn't work. Like, you don't use that rule.
Oh, you're trying. I don't know if that number's right. They have another 8 up there.
Yeah, I think one of them's supposed to be.
I'll have to look and see. What is? Here's a real periodic table. Yeah, it is 8.
So, does it not work for that one, or what?
1b and 2b. How would you get 8 out of this?
Well, because 8 is a cobalt, Roman numeral.
Yeah. So where does it? That 1 goes up. That's weird. That's weird.
When I didn't even count over. I just knew it was supposed to be 8. So
Yeah.
I had 3d6. So
Yeah, I don't know. That's weird. That's not going to be a valence question. Okay. Oh, we have too high a tie. Eric was the tie. I was going to make him do rock, paper, scissors, but he might hurt Monica. Where's Monica Lopez? Got high score. All right, so you can grab your exam and have a good weekend. Congratulations, Monica.